Okay, so this side Naveen Kumar, we need to see today electric field intensity. We will find electric field intensity due to a line of charge. Due to a line of charge. Okay, so firstly, before starting the derivation of electric field intensity due to a line of charge at a point, we need to first understand what are charge densities. So density we know, we denote it by D. D is equals to mass by volume. So this is the point of confusion for many of the students, that this is mass density, but apart from mass density there are also many type of densities like lambda, which is linear charge density, means charge upon length. So it's not necessary that always density means you have to use volume in the denominator. If we are considering 1D system, so this denominator consists of 1D units. Okay, this is linear charge density. Lambda stands for linear charge density. Okay, next one is, so you have to remember this one till the last of the derivation. Also there are also many type of densities like sigma, which is surface charge density, q by area. So this time area, we are using area 2D unit in the denominator, therefore it is known as surface charge density. Okay, and the last one is rho, means volume charge density. This time we are using volume in the denominator since we are considering 3D unit. So this is volume charge density. But in this derivation we are trying to find electric field at a point due to a line of charge. So this line, this stands for 1D dimension. It has one dimension only. So the density due to this charge will be also in 1D. Therefore we will use lambda as the charge density. In this case, we will use this first one. Clear? Okay. So to find out the charge density, to find out the electric field intensity due to a line charge, we need to first draw the line charge. We need to draw the line of charge, dot dot dot, similarly dot dot dot, and then what we have to do, we have to draw a Gaussian surface, and line of charge. To find electric field intensity due to a line of charge, we have to draw a cylindrical Gaussian surface. So what is Gaussian surface? Gaussian surface is a imaginary surface. Okay, so to find out charge over here at point P, to find out electric field at point P, we have to draw that Gaussian surface. That's what I have drawn previously, but we have to draw this after we consider the point. So after considering the point, we have to draw a Gaussian surface which is passing through this particular point. This Gaussian surface should pass through this point where we need to find out the electric field intensity. Clear? Okay, so now we have to find out electric field intensity at point P. So we have to find out the direction of electric field first at point P, which is, okay, so this is a line charge, so it has only two options. Either it will send electric field lines in this direction, or in this direction. No other option. So only sideways. If you have seen a tube light, it will only throw the lights from its curved surface. So similarly. Okay, so at point P, electric field due to line charge is in this direction, and we need to draw a area vector So area vector will be perpendicular to the surface, as I have drawn a area element. This is called area element. What I am drawing around point P is area element, and we denote it as dA vector, and E vector. And we also consider some points over this base and this base, but on the upper base the electric field is also in this direction, and on the lower base it is also in this direction, electric field. But on the upper surface the the area vector will be perpendicular to the surface, that is in this direction, dA vector. So the angle between dA and E is 90 degrees, so it will get cancelled. So no contribution of the upper point, I mean no flux is getting out from the upper surface. And similarly in the lower surface the area vector is in downward direction, dA vector, so no flux through the lower base also. Clear? Okay. So lower and upper base are not contributing in the flux. Okay. Only this point is contributing towards giving us flux. Okay, so let me delete this. Okay, so we know from Gauss theorem that flux phi is integration E dot ds. Clear? E dot ds, and there should be a vector sign since we are using the dot product. Okay, so phi means Q by epsilon naught. From the Gauss theorem we know that the total flux is 1 by epsilon naught times the total charge enclosed in that area. So this is closed integral. Okay, so E dot ds, closed integral. We need to break this dot product. So E ds or dA, we had used A, so E dA cos theta. Now cos is, and the theta was 0, right? For the line charge what we have seen, this was the point of consideration. P, E is in this direction, also dA is in this direction, so theta will be 0, in between E and area vector. So cos 0 degree, and cos 0 is 1. So Q by epsilon naught is equals to E, and E is constant, E dA, and cos 0 is 1. So now what is Q? We had recently seen that lambda is equals to Q by L. So from here in this case we can easily say that Q is equals to lambda into L. Clear? Okay, lambda into L. We will use this over here. Let me rub this. Okay, so lambda into L by epsilon naught is equals to E, and what is integration of dA? So this area denotes the curved surface, only the curved surface of the cylinder, because the upper base and the lower base were not contributing in giving the flux. So therefore this dA small area element, when we integrate it, it will give the whole curved surface area of the cylinder. So after integrating we will get, so area of curved surface area of a cylinder, we know from the class 10th level, it is 2 pi RL, right? Isn't it? 2 pi RL. So what is R and L? R is the radius of the Gaussian cylinder, what we have drawn in green color, and the L is the length of the cylinder, Gaussian cylinder, imaginary cylinder. So the formula will be, so wait, we have something over here too. This L will get cancelled with this L, so E will be lambda. So this L is cancelled, lambda by 2 pi R into epsilon naught. Clear? This was the final formula. This is the final formula what we are trying to find. So we can write it we can write it in another form too. Wait a minute. We can write it in this form too. E is equals to if we multiply 2 in the denominator and numerator both sides, we will get 2 lambda by 4 pi epsilon naught into R. Clear? I hope I'm not missing anything. Okay, so finally E is equals to 1 by 4 pi epsilon naught into 2 lambda by R. So this is the final formula. Why we had multiplied 2 on both numerator and denominator? Because we need this constant, because in electrostatics we had seen in Coulomb's law and or in electric field intensity, this constant was common. This constant was common. So we are trying to find a formula which resembles those formulas which you had learned previously in the previous chapters, like Coulomb's law or electric field intensity. In these chapters we had seen every formula in this format, which has a constant 1 by 4 pi epsilon naught. So to bring this formula 2 in that format, we have to multiply 2 in the numerator and denominator both. So this is the required formula. Thank you.